Thank you very much. I will share my screen and let me know if the slides. Wait a minute.
Yes, we see it. Yes, thank you.
You see, and does does the slide is passing?
The first
Is it
slide we
moving?
see. Not yet.
Yes?
We only see the first slide now.
You are only in the first, then, wait a minute, I will, let me be back here. I will not put it in full screen, sorry. I think in that way it will pass.
Now we see you again. Okay, now it moves.
And
yes,
there you can see it moving?
Yes, we see it moving.
Okay,
yes.
then I will leave it
Thank
there
you.
so you can see it moving. Okay. Okay, good afternoon. I am Ana Elias from the University of Tucuman, Argentina. Thank you very much for the invitation to participate at this event. I would have really liked to be there personally, but unluckily due to some travel limitations in Argentina due to the pandemic situation, I decided to be present virtually. The title of my talk is Solar Influence on Long-Term Changes in the Lower and Upper Atmosphere. Here is the outline of my presentation. I will give first an introduction to this topic and mention some results on anthropogenic and natural forcing effects, followed by a very brief description of long-term trend detection in the atmosphere and on some solar variability features. We will see then some results of works I have been involved on solar influences as a natural forcing and also as a proxy, and finally the discussion and conclusions. We begin then with the introduction. Here we have a definition of climate change given by the IPCC, which I like the most. And from it, I would like to highlight that it refers to any change in climate over time, whether due to natural variability or as a result of human activity. These two sources of climate change, natural and anthropogenic, which I will call also long-term change or trends, can be specified more. In the case of anthropogenic, we have, for example, increasing greenhouse gases like CO2, deforestation, and more. In the case of natural sources, we have long-term trends in solar activity, long-term trends in geomagnetic activity, secular variation of the Earth's magnetic field, internal factors like volcanic eruptions, and many more. The first two highlighted here are of solar origin. Trends have already been detected through modeling and from experimental data. Here is an example of these trends in the lower atmosphere. I am showing this figure from an IPCC report. Here we can see the global average surface temperature long-term trend in the upper panel, the global average sea level in the middle, and the northern hemisphere snow cover for spring. Trends like these in general have been and are attributed to anthropogenic effects. However, the sun as a climate trend forcing has been always considered, and in particular since the publication of the 1991 paper by Fritz Kirstensen and Lassen, it has regained popularity as a climate change important source in the lower atmosphere, or at least it is the paper that made me decide myself to dedicate to this research topic. Their key point was to use the solar cycle length as a solar parameter, which has a 20-year lag with respect to traditional indices such as the sunspot number. And with this, they obtain a clear, high linear correlation with the northern hemisphere temperature, as can be noticed in this figure from their paper. Their explanation was based on the following. For the lower atmosphere, the total solar irradiance would be one of the most important solar outputs. We all know that this irradiance variability along the solar activity quasi-decadal cycle, which is the most notorious, is not more than 0.1% and would not be enough to induce lower atmosphere changes according to models. However, the Gleisberg cycle of 80 to 90 year periodicity could be more effective, and solar cycle length would be an efficient measure of it. According to this parameter, we have that short cycles correspond to higher solar activity, while long cycles to lower activity. Now, the problem is, as always, which would be the physical mechanism for this high correlation. A plausible explanation would be an indirect effect of solar variability linked to galactic cosmic rays and their role as clouds nucleators. Very simplified, we have that higher solar activity implies less galactic cosmic rays, and this means less clouds of the type that induce temperature increase, and vice versa. There are statistical evidences of this based on cloud and galactic cosmic rays, measurements which I did not include here. But again, as always, we may ask, but is the galactic cosmic ray flux directly affecting the climate or merely acting as a proxy for variations of the solar irradiance or spectral components such as UV? Moving now to the upper atmosphere, which covers the thermosphere and ionosphere. This topic gained importance since the pioneer paper by Rowell and Dickinson in 1989, in which they obtained through modeling the expected effects of greenhouse gases concentration increase in this atmospheric layer. These are cooling, density decrease, and shrinking the thermosphere. This would result in ionospheric layers lowering, E layer electron density increase, and F2 layer electron density decrease. Very briefly, to those who are not familiar with the ionosphere, it is the region where there are free charges, electrons and ions, enough to affect electromagnetic radio wave propagation. This charge density is produced mainly by solar UV and EUV radiation, so unlike the troposphere, it is a region highly sensitive to the solar forcing. Here, I am showing more recent results from modeling by Solomon et al., which indicate the cooling in the upper atmosphere shrinking and the electron density effects in the ionosphere as a result of the greenhouse gases effect. The experimental counterpart to this was that the trends obtained from ionospheric measurements after filtering the strong solar effect was not globally uniform as expected, and the trend values were not completely consistent. It appeared then as possible trend forcings in this atmospheric layer, the solar long-term variation of timescales longer than the decadal cycle, bad solar filtering, which is a critical first step in trend detection in the upper atmosphere, and the Earth's magnetic field secular variation, which, by the way, is another main research topic I work on. Let's move now briefly to trend detection and some solar variability features. What do we certainly know? That there are anthropogenic and natural forcing mechanisms that are able to induce long-term changes in all the layers of the atmosphere, which we call climate change. Since a response to any source of variation can be analyzed theoretically and/or experimentally, to detect trends due to solar forcing or any other forcing, we can make it through physics, which must be followed by experimental proofs, or we can make it applying statistical methods to experimental data, followed, of course, by a physical explanation of the results obtained. Here, I would like to highlight that in the case of experimental detection, special care should be taken with forcing proxies or indices and statistical methods applied for trend detection. The solar forcing can act through changes in the output of the sun in all forms, light or electromagnetic output in general, solar wind, and energetic particles, and also geomagnetic activity, which consists in geomagnetic storms, substorms, and aurora, and is more linked to energetic particles injection during strong activity periods. There is not a clear difference between them, but we can see here we have the plot of the sunspot number as a solar activity proxies and the AA index, which is in red, which have identical time variation but not exactly Similar but not identical, sorry. Solar and geomagnetic activity have many characteristic periodicities, short terms like the 27-day rotational period, the semi-annual variation, the quasi-decadal cycle, the 22-year magnetic polarity cycle, and longer oscillations such as the Gleisberg cycle and the Suez cycle. In timescales of 10 years and shorter, solar and geomagnetic activity present differences, as can be noticed in this figure, but when we move to longer timescales, they are very similar, as we can see in this figure, where we have the sunspot number and the AA index after a 10-year moving average. Here to the left, I am showing, just to emphasize, the change in the atmosphere sensitivity to solar changes in the decadal cycle, the neutral temperature height profile for low and solar activity, for low and high solar activity, and it can be clearly seen that it's strongly, here we have almost no effect, but it has a strong effect in the upper atmosphere beginning at 100 kilometer height. Let's move now to some results I've been working on solar influences as a natural forcing and as a proxy. From this paper by Heredia et al. From 2019, I am showing here the time variation of the 11-year running mean of the total annual precipitation of a southern hemisphere station in black, and the solar barycentric distance are in red, where a clear statistical association can be noticed since 1950-1960. In this work, we analyzed Tucuman climatic series detecting an overall warming and augmented precipitation tendencies possibly linked to increasing greenhouse gases concentration. And in addition, we identified a relatively strong 20-year oscillation after the 1950s, as we can see here, linked to the planetary hypothesis of the solar cycles. This hypothesis supposes that the barycentric dynamics of the sun could be involved in modulations of the intrinsic solar magnetic and radiative output cycles, and therefore earthbound climatic responses. These results belongs to an undergraduate thesis under my direction, where the association between the North Atlantic Oscillation and the geomagnetic activity is shown. The figures show the experimental data analysis where a clear, strong, and significant linear association is evident beginning in 1950, where we can see here we have the smooth data series, and much more clearer in this one. Stronger geomagnetic activity implies, the mechanism is shown here. Strong geomagnetic activity imply an increase in NO components, which help ozone destruction. This means less ozone, a cooler polar stratosphere, a stronger polar jet, and consequently a stronger positive North Atlantic oscillation phase. A problem would be the decrease or almost inverse correlation, which we can see here previous to 1950, but at least in the last decades, it explains it very clearly. Here is part of the results shown in a very recent paper. How much has the sun influenced northern hemisphere temperature trends, an ongoing debate, where 16 different estimates of the changes in the total solar irradiance were considered. Here are they, together with 5 independent northern hemisphere temperature estimations. Here are the temperature estimations. And global warming since the 19th century is observed in all the time series. In order to assess the role of the solar forcing and to compare with the anthropogenic forces, temperature time series were first fit linearly to the total solar irradiance, and then the residuals were fit to the anthropogenic forcing time series. The total linear temperature trends are plotted as blue bars in all these figures, one per each solar activity proxy. And the left bar to each of the blue ones, we have the linear temperature trend of the combined solar plus anthropogenic feeds, and we have solar in yellow and anthropogenic forcing in gray. It can be clearly noticed that the estimated role of the sun, that is the size of the yellow bar in each of these figures, depends on the solar data series used. for trend estimation. And this is a key result, especially in the search of trend sources. From these figures, we can see that it can have a really strong role, as we can see in some of these bars, or maybe no role at all. And here I want to mention some results for the upper atmosphere. In this case, we have a twofold problem. The sun has a strong influence in the upper atmosphere trend, and since this layer is so sensitive to its shorter scale variability, it can affect the estimation of these trends through bad filtering. This problem is similar to the previous one I just mentioned, where bad choice of the total solar irradiance database can lead to wrong conclusions. The results I am showing here belong to an article which has just been accepted for publication. Here we analyze the long-term trends in the F2 critical frequency, which is a measure of the peak ionospheric electron density. As before, we are interested in long-term scales, so the first step is to filter the decadal cycle. Here we can see the filter series for 3 different stations and using different solar activity proxies. At first sight, we could tell that the first 2 stations present a decreasing trend, which would be in agreement with the increasing greenhouse gases content. However, the last station shows an increase, which is not in agreement with the greenhouse gases concentration. This station is Iowa. And again, the solar influence comes for an explanation here. We have here in this figure superposition of the 4 minima considering the 12-month running mean of sunspot number as an example, and the solid line, this one is for the minimum between cycles 21 and 22, dashed between 22 and 23, dotted between 23 and 24, and those dashed the last minimum, which are these last 2 curves. We can clearly notice that the last 2 minima are lower than the previous 2 and longer in duration also, and this somehow could induce ionospheric trends which evidently are not filtered through the traditional methods and appear as decreasing trends as those expected from greenhouse gases also. Here I would like to comment on the solar influence, which in fact is not a true physical influence, but is linked to its bad filtering from ionospheric parameters and may result in trends which are not real, but just a byproduct of the detection method. FOF2 at some station during solar cycle 23 were higher than expected. Here is the solar cycle 23 with this circle. And FOF2 is the black curve, is higher than that would be expected from solar activity. So this ends in systematic positive residuals, and finally we could obtain a positive trend which is not really induced by the sun, but is induced by the sun filtering procedure, which in this case is not adequate. But well, it's another, the sun here is also like the responsible for the trend we obtain. Okay, and finally, let's move to the discussion and conclusions. First, model considering physics and statistics considering experimental data both tell us that the lower and upper atmosphere respond to long-term solar variation. Second, the lower atmosphere is a more complex system with many interactions, and as such, the solar climate variability is still controversial and needs more results and analysis. Third, the upper atmosphere is highly affected by solar variability in short and long-term scales. And last, in addition to the true solar influence in the atmosphere, its experimental detection can be hindered by statistical procedures and/or a bad choice of the solar proxy used to measure it. Why is it important to understand and measure the atmosphere response to solar variation? Well, we live in the Earth and we want to understand and predict the atmosphere behavior, which is essential for human life. Okay, thank you very, very much for your attention.
Thank you. Thank you, Anna. Thank you very much. And so do you have still some time for the Q&A? Do you?
Yes, yes.
Okay, excellent. So, I guess die Fragen können auf Deutsch gestellt werden. Was it too much science, I guess? Okay, eine Professor Lüdecke.
Thank you very much for your very interesting speech. In the last fall, you made the remark that your results could be hindered by statistical procedures. I don't understand this. Can you explain it, perhaps, what you mean with this?
Yes, in particular in the upper atmosphere, we have, in order to detect trends, linked long-term trends, I mean longer than the decadal cycle of the sun, we have to make some filterings. And I think we all know that when we filter time series, we can induce some spurious variations which are not inherent to the time series itself. In particular, the solar field, the solar activity filtering from ionospheric data is done through a linear correlation with solar activity itself. And we do not have measurements of the true solar forcing, which is the extreme ultraviolet radiation. We use proxies for that. And proxies vary like EUV, but not identical to EUV. So when we do that kind of filtering, we are somehow inducing maybe some spurious variation which are not inherent to the EUV. And then after that, to that filter series, you apply the filtering procedure. And what I call also a statistical problem is, for example, in the paper I have just shown you on the trends in the Northern Hemisphere, where the trend depends on the total solar irradiance database that you used. I think that is, again, like a kind of statistical issue because it depends on the time series you choose. That is what I would call statistical, like trends, like have statistical problems, I would say.
Okay, thank you.
Does that answer you?
I think I understood your statistical problems. You mean somehow statistical artifacts by the method.
Yes.
But I have another question. You suggested an index instead of the sunspot number, an AA index, and maybe it was too fast for me, but I didn't get what you meant by AA index. Can you explain on that one more time, please?
Yes, the AA index is an index which shows the time variation of the geomagnetic activity. Even though it is similar, well, it is induced by the sun, of course, but it has not identical variation with the solar activity. For example, if you compare the sunspot number and AA index, unless you go to very long time scales, they are not identical. And the geomagnetic activity would be also, for example, there are many papers that argue that it is the geomagnetic activity, for example, which alters tropospheric circulation patterns. And if you use the sunspot number as an index, you will not get any correlation. While if you use AA, I used AA index as an example, but there are many other geomagnetic activity index, maybe AP, KP, or DST. They vary like the solar activity, but not 100% equal. So your results will vary with the index depending on the index you choose.
Okay. Die Fragen können auf Deutsch gestellt werden, das muss nicht auf Englisch sein. Okay, war das erschöpfend? Okay, Anna, wait, there's one in the front.
Okay.
Sorry for being late. I would like to come back to the basics, the very basics. When we look at the discussion about climate change, there is one party says this is mainly sun-driven. And others say this has something to do with carbon dioxide and whatsoever. I think the reality is a mixture of both. Can you give us a rough figure, approximation, how much of the climate change is driven by the sun and how much is driven by other factors?
Well, I don't know if I can really separate them based only on statistics. I have seen that, for example, the sun or the geomagnetic activity, which in the very last in the last decades have had an almost linear trend. And when one tries to detect it statistically, if you filter first, for example, the solar activity, you remain with no trend, and then you check for anthropogenic activity and you see nothing. And if you do this all the other way, you first filtered a trend according to the increase in CO2, then you're left with no trend. But maybe the trend, unless you know physically which one is the responsible, I think that it is very hard to say, to attribute which one is more responsible, at least for me. And in the ionosphere, maybe can be more clear, but not. I am not really sure I can say which one is more responsible than the other. But the thing is, in the upper atmosphere, sometimes the sun has a more clear signal than in the lower atmosphere. But statistically, I have not found yet how to really separate them.
I think there's one more.
Sorry.
It seems to me that there's a noise in terms of sea currents and things like that have a much bigger amplitude than the slow change of climate given either by the sun or by the greenhouse gases. So, I mean, somehow it's very difficult. I see it's very difficult to find what is really climate change and what is cycles from mainly ocean currents. Do you have any comment on that?
You mean, sorry, I didn't understand the last part. You mean that it is really, can you repeat the last part only?
Well, I would say that, so to say, internal variations mainly due to ocean currents is like a noise that spoils, it makes it very, very difficult to find. You have to, that when you say filtering, you have to filter out all these fast changes which are of a much bigger than the slow change.
Yes, well, that I think that this is a very important issue, because in order to filter this, you have to manipulate the series. And again, we are with the problem that I just mentioned that happens with the ionosphere and also with the troposphere. We do not have that kind of problem, at least in the upper atmosphere, that internal interaction. We do not have that problem. But we have the problem of the decadal cycle of the solar activity. And in the case in the troposphere, well, I think it presents two problems. Physical, because maybe it has a stronger effect than we think, and in our attempt to filter them, we completely, maybe we are not filtering them well, or we are completely making them null, but through our procedures. So again, it's the same problem as the one with separating two sources which vary very similarly. And the other problem, I think, not only is the filtering problem and all that, but it's the amount of the response of our system. It's so small in comparison with other natural variations that makes us even harder to obtain statistically significant results. That's another problem, no? The amount of the response. The long-term solar effect and the greenhouse gases effect, they are all really, really small. So that's another problem, I think.
Okay, Anna, thanks a lot. Thanks a lot for your contribution and for this exhausting answers.
Thank you.
And thanks for making really time in your schedule for us, and all the best.
Thank you for allowing me to give this speak at this time.
Thank you.
I really appreciate it.
Okay, bye. Super.